Okay, welcome back, everyone. So the second talk of the day is from Lara Anderson from Virginia Tech, and she'll be telling us about SU3 holonomy and SU3 structure metrics from machine learning. Take it away, Lara.
Thank you very much. So thank you to the organizers for the invitation to participate in this workshop. I think this is a very interesting set of topics, and I've enjoyed all the talks so far. So as it says in the title here, I'm going to be talking about approaches to SU3 holonomy and SU3 structure metrics, utilizing techniques from machine learning. This will be based on a paper that was done in collaboration with James Gray and Nikhil Raghuram, also at Virginia Tech, Mattis Gerdes and Sven Krippendorf in Munich, and Fabian Rühle at CERN. And this paper came out in December of last year. I'd like to flag right at the beginning that there's a wide range of questions that we sort of touched on in this paper. And in anything to do with machine learning, there is very much an art as well as an expertise to setting up these networks and to actually making this stuff work. And this was my first paper, first project to sort of touch on these techniques. However, Sven and Fabian have had each had a very extensive program of research in this area and have developed lots of really great tools. So the credit really goes to Sven and Fabian for their expertise in this subject. Also, as was flagged in Mike's talk, as you know, there were several groups that were thinking about related things around the same time. So as Mike mentioned yesterday, there was a paper by him and his collaborators that we actually coordinated release of at the same time in December. And unbeknownst to us, the group led by Jajala et al. Was also working on similar things. We knew that they were working on machine learning techniques, but I mistakenly thought they were working on Ricci-flat. Turned out they were also doing very similar things, and they submitted their paper just very shortly after ours. So really 3 works on similar topics all appeared at the same time. Great. Okay, so a bit of motivation to start. I am a string theorist, and my primary motivation is that in the process of string dimensional reductions, the metric is a crucial bit of information to determine low energy effective physics from string theory. And indeed, if you're just sort of thinking of this in a vacuum as a theorist, the metric is such an essential ingredient in specifying the theory that it seems actually quite remarkable that string theorists for the last 30 years have found so many things to say without direct knowledge of the metric on the full solution that they were looking at. But just to highlight a few examples of things that depend crucially on this data, as was mentioned in yesterday's talk as well, Yukawa couplings in heterodic string theory represent trilinear couplings between fields in the 4-dimensional effective theory. These depend on both gauge fields and connections on vector bundles over these extra dimensions. The normalization of coefficients and the exact value of, for example, the mass of the electron in a string vacuum would depend on knowledge of the metric. The matter field Kähler potential, very similarly, is unknown except in special cases and makes fully specifying, for example, a heterodic theory very difficult. Although we can count the number of zero modes of massless states, actually determining the harmonic representatives of the cohomology classes that count these is something that is a metric-dependent problem. Involves solving for modes of V-twisted Dirac operators, which again would depend on the knowledge of a connection on a vector bundle and a metric. And as Mike mentioned also yesterday, problems in moduli stabilization are one that is of long-standing interest in string theory. Being able to specify physical vacua is something that, of course, we are very interested in, and knowledge of the metric would be useful for that too. So broadly, the question, how is one going to find the metric on manifolds of interest to string dimensional reductions and connections on bundles as well? At the moment, there are very few analytic techniques that are understood, and those only in very special cases. So really, numeric methods seem the primary way forward in terms of trying to obtain this data for a serious study in string theory. So to begin this, the context of geometries that I want to begin talking about is SU3 holonomy manifolds. And for the purposes of this talk, I'm going to define a Calabi-Yau threefold as a complex manifold that admits 2 structures, a nowhere vanishing real 2-form J and a complex 3-form omega that satisfy the equations that are laid out here. Both of these objects are closed, and they satisfy the following relationships with each other. Now, as we all know, Yau's theorem guarantees existence of a Ricci-flat metric associated to such a structure that is unique if the moduli, i.e. the point in the parameter space of the metric, is fixed. But knowing that explicitly is something, of course, that we don't have. A quick aside, for Calabi-Yau threefolds that will appear in this talk, an explicit expression is actually known for the holomorphic three form, capital omega. And we'll come back to that in a second. So, oops, sorry. A couple of facts for this talk. I'm going to be interested in Calabi-Yau threefolds. So these are 6 real-dimensional manifolds, complex threefolds, and these are algebraic. Metric deformations are parameterized by the Kähler and complex structure moduli that are counted by the Hodge numbers H11 and H21. And the simplest examples of such things are complete intersection manifolds in complex projective spaces, for example, or more generally, complete intersections in toric varieties. The simplest example that everyone starts with in trying new techniques is the Quintet Hypersurface, which already made an appearance in Mike's talk yesterday. An example of that is a degree 5 hypersurface in CP4. Here, the Z's are the complex homogeneous coordinates on the ambient space CP4, and a single polynomial relation that in principle could be a function of 101 complex parameters. Here, I've just illustrated with a single complex parameter, the so-called Fermat quintic. As I mentioned on the previous slide, the holomorphic three form can be constructed explicitly in such a case, where if we are given the vanishing locus of a polynomial of this type, there's a simple algebraic description for the holomorphic three form that can be constructed patch by patch on the complex manifold. So I have here a little bit of motivation in terms of the idea that has been behind numeric approximations to Calabi-Yau metrics to date. A lot of this was covered much more clearly and in depth in Simon's talk yesterday, so I'll do this fairly quickly. But the loose idea is that there is, in some sense, a natural set of Kähler potentials for defining the Kähler Calabi-Yau metric. So for Calabi-Yau manifolds, we always have an embedding into some large projective space. The Kodaira embedding defines such an embedding via the global sections of some ample line bundle that is defined over the Calabi-Yau X. And we can use that space of global sections as a parameterization for metrics. So on the large projective space that we would be mapping into, there is a natural metric, the Fubini-Studi metric, which is defined here. This would just be the log of mod z squared, and this can be generalized by adding in a Hermitian matrix Hij. So these metrics are nice metrics on the space in which we can embed, and they can be restricted to the Calabi-Yau, but of course are not Ricci-flat. So as outlined in Simon's talk, the idea is in terms of this natural embedding, we can try and write down this generalized Fubini-Studi Kähler potential, and to consider it first as its action as a fiber metric, a Hermitian fiber metric, on the line bundle L to the power k. So this provides a natural inner product on the space of global sections defined here, and this integral naturally is done over the volume of the Calabi-Yau threefold. So again, all of this made an appearance in Simon's talk yesterday. So what is the idea with these ingredients? We have a natural generalized Fubini-Studi metric. We view it as a Hermitian metric on a line bundle. And then the interesting thing here is that such metrics on ample line bundles can in some sense provide a basis of Kähler metrics on the Calabi-Yau. So this result due to Tian, and there's quite a bit of other literature, again, that was reviewed in Simon's talk, is that we can view this generalized Fubini-Studi metric as being dense in the space of Kähler potentials. So the very rough idea is that we could try and use these to approximate the metric of our choice, but how to find the right path to a Ricci-flat metric on the Calabi-Yau threefold. And this, again, reviewed yesterday. So in this context, this is where the ideas of Simon's theorem and balance metrics appear. So balance metrics provide a nice tool for having a well-controlled and guaranteed convergent path towards the metric of our choice. So we refer to a Hermitian fiber metric H on a line bundle as balanced if this metric on the space of sections inverse is equal to the H that appears in the generalized Fubini-Studi. So just going back one here. So here is the definition of sorry. Where did we go? There we go. Here's M. So, and H is the guy that appears in here. So if M inverse is equal to H, then the metric is called balanced. This is the idea behind Donaldson's T operator. which is that the T operator can be iterated in order to find this balanced point. There's many theorems about balanced metrics, and this one, as was reviewed yesterday, is a crucial one. So for each k greater than or equal to 1, the balanced metric on this line bundle exists and is unique, and as k goes to infinity, the sequence of metrics that you would produce can converge to the unique Ricci-flat metric for a given Kähler class in complex structure. Okay, again, well understood from Simon and from Mike's talk yesterday. Here is the basic set of steps in what I will refer to as the Donaldson algorithm that could be implemented numerically. And indeed, this was done by Mike and collaborators and also by work of Brown, Urwit, and collaborators about a decade ago. The idea is, beginning with a Calabi-Yau threefold, you can choose an ample line bundle and a given degree k that you'll be working to. That's a twisting of the line bundle L to the tensor k. And which point we're going to compute a balance metric, which will approximate the Calabi-Yau metric to some accuracy. Very roughly, the mod of the Ricci scalar is going to fall off like 1 over k. I'll talk more about that in a second. But as you increase k, this will become smaller and smaller. To actually teach a computer to do this, you have to calculate a basis of global sections at each value k for the line bundle, the ample line bundle of your choosing. You choose an initial non-singular Hermitian matrix to define the inner product on the space of sections, perform the numerical integration to compute the T operator, set the new h to be your previous h, i.e. iterate, and you return to this step and repeat until you reach a fixed point of the T operator. In practice, the T operator convergence occurs in about 10 iterations or less and does not depend too sensitively on the initial choice of a Hermitian fiber metric. You can then increment k and repeat all steps until your desired accuracy is reached. Okay, so as I said, this was stuff that was first tried about a decade ago. And this is a sample plot from a paper of mine from about a decade ago where we were trying this kind of thing. And the thing that is plotted here, the one to focus on, is the mod k of the Ricci scalar itself. And you can see that as you iterate k, this is indeed getting smaller. So good start. Predicted fall off you can be compared to going roughly 1 over k as you choose a power of the line bundle. So this was sort of the state of the art in the field as of the last 10 years. And as you have heard from yesterday's talk, the question is whether new numeric approaches, for example, those from machine learning, can substantially improve upon the implementations that were developed about a decade ago. So what are some of the ideas that one needs to ask in this context? For a given approximation, you can say that to a certain accuracy, you could choose a sufficiently high k, iterate the T operator to converge, and ask, did you find a numeric approximation that was, quote, good enough? Now, the hard part with this is that the calculation that I just very schematically outlined, as it was developed a decade ago, is extremely computationally expensive, running on supercomputer clusters over many months to produce metrics at a single point in moduli space. So the question of, is this actually a good enough numeric approximation for the applications that you would like to use it for string theory? The answer is we don't really know quite how good it has to be because the computational difficulty has been such that this has not actually been pushed forward to compute all the things you would need for a physical application. So we'll touch more on this in a moment, but this is a tricky question in terms of what is exactly good enough. Note that other approaches to metric approximation do exist in the literature, and I'm going to mention another one shortly. But here's the plan for the rest of the talk. With this broad overview of the Donaldson algorithm in hand and the state of the art as of the last 10 years, my collaborators and I wanted to ask the question of, can machine learning techniques be applied in this context and to improve upon the accuracy? And in particular, we were interested in two things that we hope to generalize beyond the Donaldson algorithm as it had previously existed. We were interested in the problem of moduli dependence, which was extremely computationally prohibitive in the previous approaches, and also ways to generalize these techniques away from the pure SU3 holonomy case into more general SU3 structure manifolds or perhaps other exceptional holonomy manifolds. So the plan for the rest of the talk, I'm going to describe approaches to supervised learning of moduli dependence in Calabi-Yau metrics using the Donaldson algorithm to generate training data. Direct learning of moduli dependent Calabi-Yau metrics, both with and without the Donaldson ansatz. And then moving away from the Kähler regime entirely, I'm going to discuss direct learning of metrics associated to SU3 structures. So that is the idea. So to begin, as I've already mentioned, for most applications within string theory, we really need to know the metric as a function of moduli. Now, the problem with using the Donaldson algorithm for this is that the metric, as I described it, as built as a Hermitian structure on the space of global sections of some line bundle, is that the moduli dependence of the underlying Calabi-Yau can enter in a rather subtle way. Specifically, it enters through the choice of the particular polynomial Calabi-Yau that we choose and the way that it is discretized in iterating the T operator. And in addition, the algorithm, as I already mentioned, is extremely computationally costly. So if you're going to run it for 2 months on a supercomputer cluster, running it for different values of the moduli to try and somehow extrapolate moduli dependence is prohibitively slow. So the first idea is, can the moduli dependence of the metric using Donaldson's algorithm be learned using supervised learning with training data produced by the Donaldson algorithm? So we'll turn to that first. So here's the procedure. Imagine that we compute the fiber metric H for different choices of the complex structure using Donaldson's algorithm as the training data. In particular, we used a sample of 80,000 points over the Calabi-Yau and chose the level of the Donaldson algorithm at k equals 3 and demanded iteration of the T operator to converge to the 10 to the minus 6 level. The input for the neural network then was for the Fermat quintic that I outlined earlier, starting at the simplest possible case. 3 numbers, real and imaginary part, and mod of sigma. And the output is the real and imaginary parts of this Hermitian metric. This is, as it turns out, not very sensitive to the hyperparameter tuning of the network and did not require complicated network architecture. I won't go into the details of that architecture, but Mike outlined the basic structure of a layered network, feed-forward network very nicely in his talk yesterday. A few details about this, about 3 hidden layers, the number of nodes, and the type of activation function that were used are provided here. So basic idea, we are training a machine learning network to minimize an error measure. In this case, the error measure chosen, again, very similar to the one that was shown in Mike's talk. This is what I will refer to as a Mange-Ampere error measure. This is comparing the fact that for SU3 holonomy manifolds, the top forms should be, as defined by the holomorphic 3 form and 2 form, should be the same. And so you can demand that these two agree over the Calabi-Yau in order to tune your network towards the Ricci-flat solution. So within this, this approach, here is the type of data that we were able to produce. So in this first image, we have values of the complex structure parameter, real and imaginary parts. The blue dots are the training data, so the values of the complex structure that the network was trained on. So these are, Donaldson algorithm was 1, a metric was produced for those values. The neural network then produces new Hermitian fiber metrics and hence Calabi-Yau metrics at other values of the complex parameters. And we can compare several things here. So in this plot on the right, the actual error measure, so the deviation away from Ricci flatness is shown both for the Donaldson algorithm for the test data, the neural network prediction for other values of the complex structure. And then this nearest value idea is you can ask, if I just perturb the complex structure a little bit, but used the Hermitian matrix H that I had from a nearby point at this other point in the complex structure space, if for nearby points, if you're sufficiently dense in the set of complex structures, you would expect this to not be too different. So this is basically a test of how much is the neural network really telling you here. And you can see that all 3 are basically on the same order of magnitude. So the prediction of Donaldson, the neural network's prediction, and then what you would have gotten had you used, quote, the wrong complex structure nearby to produce the same metric. We'll come back to this in a second and show that the neural network is actually doing much better than you would expect. But at the moment, for a sufficiently dense sample and nearby points, you can see things are consistent. This final plot on the bottom is just showing the error as plotted for different values of the real and imaginary parts of sigma. And one thing you can note is that as the complex structure gets bigger, the error goes up for larger values of psi. So this is telling you that in order to achieve a comparable level of accuracy, At higher values of the complex structure, you would have to run Donaldson's algorithm to higher k in order to achieve the same level of accuracy. Now, where things get more interesting, the key point here is that the neural network's interpolation continues to work even with a sparser training set. And this is more impressive. So in this sense, now we can train on far fewer points. These are the blue dots in this diagram, and then ask the neural network to produce the metric at other points in nearby complex structure. And you can see here that the errors for the neural network stay very low. If you had just used the wrong complex structure and still computed the error from that, now it has diverged and is much bigger. So you can see that the neural network, from a very limited bit of training data, has actually won you something quite valuable in terms of higher accuracy. And this is extremely important because running the Donaldson algorithm is costly. So if we want to obtain moduli-dependent results to higher accuracy, you need to be able to divorce yourself from running the Donaldson algorithm too many times. This is also important in terms of if we wanted to work in cases with less symmetry. So what I'm referring to by symmetry here is that historically in most implementations of the Donaldson algorithm, as well as what one might try in machine learning, people have considered Calabi-Yaos with high degrees of symmetry in terms of the very finely tuned complex structure that I described earlier, and also imposing discrete symmetries on the form of that those complex structures could take to make the space of global sections more restricted and hence easier to parameterize. So if a neural network can predict the complex structure values very accurately as you move away from very symmetric points, that's a powerful advantage compared to existing implementations of Donaldson. So I illustrated this for the Fermat quintic with a single parameter. There's no in principle problem with extending these methods to other Calabi-Yau threefolds and of course higher numbers of moduli. The downside of what we just did in terms of a supervised learning experiment in which you are learning complex structure by running the Donaldson algorithm and training the neural network is that this, of course, has tied the whole process to the accuracy and computational cost of the Donaldson algorithm itself. So even if you can make do with a sparser set of training data than you might have thought, which is great, this still has its limitations. So the obvious thing to do is to try to learn the moduli-dependent metric directly, i.e. without using Donaldson's algorithm as a crutch. So let me turn to that now. So now we're going to focus on machine learning technique of direct learning of the Kähler potential. And here the balance metric output of Donaldson algorithm is at a given finite k, so not taking the full k goes to infinity limit here, is not necessarily the most accurate approximation to the Ricci-flat metric at that finite level. So the question is, can you find a better approximation to it? So instead of using Donaldson's algorithmic data, we can instead generate networks to find parameters that are trained directly using a loss function, such as the Monge-Ampere loss. I should say that sort of spiritually, this is very much an idea that appeared about a decade ago in the work of Heterodic and Nassar. Their idea was to try to directly minimize the Ricci scalar itself, i.e. Energy minimization problem, using essentially the same loss function. In their case, rather than using the techniques of machine learning, they were using a simple minimization function in Mathematica. And they found that they could obtain quite accurate numeric approximations at very symmetric points. So for very, very tuned complex structure, much more rapidly than other implementations of, for example, the Donaldson algorithm. So similar in spirit to those guys, but we're going to use neural networks to try and do this approximation. So the procedure here would be as input, we're taking components of the complex structure as a complex number. The output of will again be the Hermitian fiber metric H alpha beta bar. And in this case, it turns out to be convenient to use sublinear algebra, the Cholesky decomposition of this guy. This is in terms of triangular matrices, block triangular matrices and their Hermitian conjugates. This decomposition is used in the output as it makes it easy to ensure that this is a positive definite metric. It also leads to slightly better results than utilizing just the real and imaginary parts of this matrix directly. And the architecture of the neural network we used was very similar to what I outlined earlier, this time sigmoid activation functions, but otherwise similar in spirit. So here is a sketch of those results. So for a range optimized for values mod psi between 0 and 10, We can plot here again the Monge-Ampere error. These two different blue and orange plots are different models with a different number of hidden layers to them. And the width of the plot here is taking for the full range of complex psi, taking the max and mins of those errors. And the key points to compare to here is that you can see now the psi-dependent error measure. So how close to Ricci-flat are we getting for different values of psi? And we can compare that to, for example, what the Donaldson algorithm would have produced for us at k = 6. So choosing a fixed approximation within Donaldson. Down here, this bottom line is Donaldson at k = 12, and for one value of the complex structure, psi = 0. So the first thing to note is that the Donaldson algorithm at k = 12, this bottom line, would take order days, I would say, depending on implementation, order months, to run even for the single case of psi = 0. So you can see that the neural network is already doing quite well in that we have comparable accuracy to Donaldson. However, this network at k = 6 took only minutes and is of the same order of magnitude. Here, the shaded versus unshaded regions are, this is the region for which the neural network was actually trained, these values of psi, and this is the extrapolation to new values of psi. Once again, for higher psi, we see those errors going up. That's to be expected. But this can extrapolate quite strongly and is staying better than the extrapolated Donaldson, even at higher complex structure. We can see that over a broader range of complex structures here. And this, in my opinion, was the real sort of proof of principle that the machine learning architecture here is really buying you something new compared to previous implementations. So again, we have several models presented. Comparison here to Donaldson at k = 6, that's the green line, and this is over a wider range. So again, we see that we do better than the Donaldson algorithm in terms of lower error, and that this improvement actually extends up to around psi = 175, nearly a factor of 2 beyond the regime used in training. I won't go into the details of this, but these results appear to be strongly dependent on the network architecture, including the extrapolation into the shaded region. And there's clearly interesting questions of optimization, which were left for future work. At the moment, this was simply a point of proof of principle in our implementation. Okay, so now I want to take a step back, having done two different explorations of machine learning to essentially use the Donaldson algorithm, or at least the ansatz of the Donaldson algorithm to produce moduli dependence. We can now take a step back and say, instead of learning parameters in an ansatz for the Kähler potential, is it possible to learn the Calabi-Yau metric directly? Now, you might want to ask, why even do that? Surely, Kähler potentials are simpler than Kähler metrics. The reasons why you might want to try this is that perhaps we can improve performance by not being tied to that ansatz at a fixed k. And the more important one is that we might be able to generalize this approach to more complicated geometries, i.e. to SU3 structure, which I'll talk about in a minute. One disadvantage is that if we're not using the Kähler potential formulation and the construction of this Hermitian fiber metric on a line bundle, as was outlined previously, is that if you produce a metric, you need to check that this metric is globally well-defined in Kähler. So we did a few experiments with this. I am going to sketch only one of those here. The basic idea is that for the loss function, we're going to have different weighted components of loss that the network will try to minimize. Here, Monge-Ampere is the previous loss that I described before. So this is the ratio of the top form as formed from J and omega. And to this, I now need to add two more to ensure global Kählerity and well-definedness of the metric. The first of these is that DJ will be 0, i.e. Kähler, and what I've called L overlap here is the condition that on overlaps in the manifold, the metric pieces together correctly. So both of these should be 0 for a correct solution, in fact, all three. And we can experimentally try how these different weights should be varied in order to train the network effectively towards a Ricci-flat solution. The losses, I just said, used to ensure that the two form is closed and globally consistent. There is, in addition, a question of a so-called boost to the network. This is basically where you want to start the network at to try and ensure that it reaches a reasonable solution. So you could try starting close to a known solution like the Fabini-Studi metric and perturbing away from that. You could try this either by adding a perturbation or by multiplicative perturbation. And to me, at least, there was no sort of in principle reason why one or the other of these should be better. Experimentally, though, we found that multiplicative boosting worked best. Linear boosting didn't do much better than just using the Fubini-Studi metric, and it depended sensitively on the weighting of these different losses. So the procedure in this direct learning experiment is that the input will be the real and imaginary parts of the homogeneous coordinates describing a point in the algebraic Calabi-Yau. The output, also the complex structure, real and imaginary parts of psi. The output are the components of the metric itself at that point. So d squared real and imaginary parts of the metric at that point. So to give a concrete example, we're going to look at a case optimized at the complex structure psi equals 10 on a data set of 10,000 points. And we can split those points according to a train test ratio 90-10. We train for 20 epochs. The accuracy reaches the same level as the Donaldson algorithm at k equals 5. And we expect that if we use more points and tried to optimize that architecture, this could be improved. So here's the interesting structure, though, that one might want to explore. So if you look at each of these errors, as we train the neural network over several epochs, you can ask what happens to the loss, i.e. what happens to the net error away from Ricci-flat solution that we would consider. Here you can see the different colored dots in each case we were trying to explore essentially how important are each of the components of the loss function to the overall success of approximating the Ricci-flat metric. So for the first, if we optimize the neural network with all three losses, you can see that we have here the K-larity condition, the overlap condition, and the Monge-Ampere loss, with the total loss tracking Monge-Ampere very tightly. So from this first plot, we can see that the overlap condition, although it wasn't guaranteed for the neural network, is essentially automatically satisfied for these networks. So this was by no means the dominant contribution to the error. You can then try to turn off various elements of the loss function and ask, how does the neural network respond? So without the Kähler loss, i.e. lambda 2 equals 0, this is in the middle. And you can see here that now, if you have turned the Kähler loss off, this stays flat, and the total error is very sensitively hanging on that. So this was a crucial component of the loss function. And you can optimize without the overlap loss. Again, same comment that I made here. Turning off the overlap, again, this stays tied to the Monge-Ampere loss and does not track the overlap loss at all. So the takeaway from this experiment is we see that this is indeed converging to something. This is going down as you increase training, which is great. And we can explore the relative weighting of these different features that we are using in the direct learning. We see that the overlaps do not play much of a role. And interestingly, we can ask the question here in the case that we see for example, turning off the Kähler loss. You can see that the Kähler loss is staying static, the overall loss is staying static, but the Monge-Ampere loss is actually still tracking to something. So this is heading towards some sort of solution, and one could ask, what type of solution is it actually tracking towards? So again, quite promising that this direct learning actually seems to be doing something. And with that lead-in of what, when you drop Kählerity, is your network headed towards, this leads me naturally into the question of having set up this technology of trying to direct learn a metric without an ansatz. The hope is that you can move away from Kähler geometry. And for me, at least, this was part of the project that I was the most excited about, because this is something very different than anything that had been attempted before, in that here we have much less analytic control, much less computational control in principle. So this is something very substantively new that machine learning techniques might be able to do for you. So in particular, moving away from the Kähler regime, the important class of geometries that I want to consider for n=1 compactifications of string theory are SU3 structure manifolds. These are 6 manifolds that, again, have a nowhere vanishing 2 form and a 3 form that obey the same algebraic relationships as the Calabi-Yau threefold case, namely that j wedge omega is 0 and j wedge j is 3i over 4 omega wedge omega bar. But their differential properties are different in the case of SU3 structure, namely neither of these forms is closed. So an SU3 structure can actually be classified by the deviation of j and omega away from being closed forms. And these are classified by the so-called torsion classes. So the deviation away from dj and d omega being 0 can be parameterized by torsion classes W1 through W5, where these torsion classes are given in terms of the defining 2 forms and 3 forms in the following way. Here, this angle bracket refers to contraction with the metric. So you can see W1 and sorry, there should be a W, yeah, that's right, W4, W5. And then here, W2 and W3 can be determined in terms of W1 through W4 via the conditions on the previous slide. Good. So string theories place different constraints on torsion classes for there to be an associated solution to the type of theory that we want. So depending on whether you're doing heterodic string theory, M theory, type 2B, you can ask what is the torsion that you can have in order to have a consistent solution. Example for heterodic string theory, the Strominger-Hull system was cleanly parameterized to show that W1 and W2 must be equal to 0. W4 is equal to a half W5, which must be D of some scalar phi, and W3 is unconstrained. In this case, for the Strominger system, the manifolds are complex, but no longer Kähler. Note that a Calabi-Yau, as I've defined it previously, is a special case of an SU3 structure manifold, namely where all the torsion classes are 0 and the forms are closed. Okay, so our goal then is to start with some well-controlled / simple example of SU3 structure. And the observation that we made in order to have sort of the easiest possible SU3 structure cases to consider is that some Calabi-Yau manifolds admit not only Ricci-flat metrics, but also other SU3 structures as well. So if you have a manifold, for example, the Quintet, that admits a Ricci-flat metric, there's nothing that stops you from putting a non-Ricci-flat metric that obeys the conditions to be an SU3 structure on that same manifold. And in very nice work by Larfors, Lucas, and Rühle, Fabian also on this paper, there is a nice ansatz for one class of such SU3 structure solutions that are fairly easy to write down. So the basic idea is that we're going to use the J and omega that we can simply write down for one of these algebraic threefolds, but deviate away from the Calabi-Yau choice. So here in their paper, they were considering Calabi-Yaus that were formed as a complete intersection in a product of ordinary projective spaces. Note there are 7,890 such manifolds called CCs. And in this case, they have a Kähler form, which is obtained by restriction of the ambient projective space Kähler forms. So here I could have higher H11, and the 3 form is taken as sort of the natural 3 form that is algebraically written down from this hypersurface description, which I had on a previous slide. But instead of writing down the natural holomorphic object, we add the 3 form and its complex conjugate together with arbitrary complex functions A1 and A2. And we consider a linear combination of the Kähler forms with some real functions, little ai. So the idea is that we're taking the sort of innate structures, J from the ambient space, Kähler forms, omega 0, the natural holomorphic 3 form, and we're going to combine and perturb these structures away from their Calabi-Yau form and ask, can we find a solution for the SU3 structure? So the resulting torsion classes are straightforward to write down based on these ingredients, and they are now all functions of the little and big a's. So the idea is that given such a combination of torsion classes, now for an ansatz of this type, we could ask that we could minimize a loss function in a neural network that was built out of these functional forms for whatever class of string theory we're interested in. I gave you the example previously of the Strominger system. We could impose the conditions on torsion classes to have the Strominger system, and we could ask to minimize a set of losses built out of this data. In principle, we could use this ansatz to learn approximate SU3 structures. And in principle as well, if we define triple intersection numbers in this way, or the analog of triple intersection numbers, then there's a relationship between the capital A's and the little a's that is pretty straightforward to compute. So what would you teach the neural network to optimize on then for this particular ansatz? For the Strominger system, you can define a set of weights as the following here. So you have a set of loss functions that are going to extremize or to minimize the conditions for SU3 structure broadly, and then the conditions on the torsion classes as I've outlined them here. These are the conditions from the previous slide. Let me go back. Sorry, that's going forward. So that's these conditions as outlined here for the Schrödinger system. This could be used to train a neural network in which you give it points of, in this case, the same algebraic manifold that we were using for the Calabi-Yau metrics, and you can receive as outputs the ingredients of your SU3 structure, in this case, phi, A's, and so on. Now, we haven't actually done this, and the reason that we didn't do this quite in this form is that if you do this, you have the question of, suppose you run this over some number of epochs, you produce an approximate metric. It now is incumbent upon you to say, do you trust the result? So are you sure, we have no existence theorem for SU3 structures the same way that we do for Yau's theorem. So we need to ask, do we actually believe that the neural network is approximating a real solution to the theory? So in order to probe that question, I want to use this same setup in a situation where we know the answer, and so we can test whether the neural network is actually doing what it's supposed to do. So the most important reason to show you this ansatz was to introduce a particular example on the quintic, which was taken from the paper by Fabian and collaborators that I mentioned earlier. So an example on the quintic, this is defined by a single hypersurface equation. These free parameters of the torsion classes can be specified here. And sorry, x's were the defining polynomials, so you get defining coordinates. In this case, this has torsion classes that satisfy what the conditions that we need for the Schrödinger system and are parameterized in terms of this A1. And this would provide a solution to heterodic string theory from this paper. So this is an analytic solution for an SU3 structure, which is great. And now the question that we can ask is, can we actually use machine learning techniques to reproduce this analytic solution and test whether the neural networks converge to the thing that you would hope they would in this case? Again, just to stress it, this check is important in that if you're using these numeric approximations without the theoretical framework of Donaldson's theorem, of Yau's theorem, of understanding convexity of these functionals and the number of minima that they might have in minimization, this is important to know what you're doing. So let's see if we can learn the two form for that known analytic solution. Omega is fixed by the algebraic form of, in this case, the quintic threefold that we're going to put this SU3 structure on. In this case, we know that W1 and W2 equals 0, W5 is 2 times ln A1. So to try and force the network towards the known solution, we need to demand that W3 is 0 and W4 is of this form. So the basic idea is we're going to use exactly the same type of network architecture and motivation behind the direct learning of the metric in the Calabi-Yau case, with the exception of replacing the Kähler condition by the following loss. So here we're going to demand that DJ is not 0, but is equal to this guy. We ran this for a choice of complex structure, psi equals 10 quintic, using multiplicative boosting again to start the metric near the Fabini studi for a known metric. And again, inputs and outputs mimic our experiment for directly learning the Calabi-Yau metric, except that now we expect to see a non-Ricci-flat metric. We can see by observing the evolution of the losses that we do indeed seem to be approaching an SU3 structure solution. So here is over a series of epochs, here's the change in the loss function. Again, so this is a typo, this should not be Kähler, but the W4 condition. We have a Monge pair, an overlap condition, and then the W4 going to 0 condition, excuse me, the DJ being non-zero condition. And we can describe the total loss, which appears to be dropping and plateauing towards something. So it's nice to see that this is evolving and headed towards some sort of output. The question that we really wanted to ask in this context is, can we verify that it's approaching the known solution and that the neural network is actually doing what you would like it to? So for that, because we actually know the metric in this case, due to the analytic form found, we can measure the difference to the known solution directly by considering a mod n norm of the difference between these two metrics. And for n equals 1, we can compare the output of the trained neural network to the Fubini studiometric. So the Fubini studiometric is not at all a solution, but you can see the sort of order of magnitude of that error point by point. And we find that that's about order 0.5 and that the neural network is performing substantially better at 0.025. So this improvement is even more pronounced for higher n norms, showing that the neural network has fewer outlying regions far from the correct value. So this is exciting. This shows that indeed you can approach a known SU3 structure solution and that there's no in principle problem to using the neural network architecture that we set up to find SU3 structure as opposed to SU3 holonomy solutions. So with that in hand, I'm going to conclude here and just say that we have presented a number of experiments. This was by no means a comprehensive list of either the things from our paper or the number of questions that you could ask in this context, but I hope I've given you some sort of outline of the types of questions that you might ask in this context. So I outlined the supervised learning of moduli-dependent collabiometrics, the direct learning of moduli-dependent collabiometrics, both using ansatzes and not, the ansatz in this case being that of Donaldson. I also discussed the direct learning of metrics associated to SU3 structures with torsion. There's clearly many other non-Calabi-Yau, i.e. Other special structure or special holonomy manifolds that you could attempt to apply these same techniques to. To our knowledge, I believe this was the first attempt at numeric approximations for SU3 structures in our work. And this application of machine learning, I hope by sort of outlining these experiments shows that at least this seems to be a promising avenue. There's much more to consider. And I hope that people will stick around for the discussion session and share ideas and open questions. And I'll stop there.
Thank you, Lara. Let's thank Lara for this clear presentation. Thank you. We have plenty of time for questions and discussion.
I understand there's some kind of theory with equations which combine a Yang-Mills connection with these SU3 structures.
That is correct. Yeah, the bundle conditions are still Hermite-Einstein.
Yes.
Yep. So still a Kobayashi-Hitchin correspondence for those stable bundles.
The same methods could have applied?
Yeah, that's a great question. So this is something, this is a natural question. I mean, particularly if I'm talking about the context of the Strominger system, whereas, as you point out, there will be bundles in the game. Certainly, as was discussed already in Mike's talk, you can try and apply exactly these same techniques. And the setup is very similar to finding Hermite-Einstein connections on stable bundles. There's no in principle problem to doing that, either using the generalization of your ansatz due to Wang for non-abelian bundles, creating Hermitian fiber metrics on those. And then you could ask whether you could do the same setup for SU3 structure, using that as the background metric on the base manifold. And again, in principle, I would think all of those, that is totally doable in principle for each of those steps.
Oh, thank you.
But sorry, Lara, just to follow up on that, how would you incorporate the kind of coupling between the problems? Like you have this sort of anomaly cancellation or whatever, this anomaly free condition or something that you also need. So
good. There is indeed topological coupling. So that choice would go into the sort of much like we're choosing an algebraic description for the manifold and then placing an SU3 structure on top of it. We would choose a topological class of bundles to specify for the solution that obeyed these conditions like anomaly cancellation that you mentioned, and then attempt to find Hermite-Einstein connections on that class. So in some sense, actually tuning yourself to the right topological region is the easy part. It's very easy to write down families of bundles that have the right properties, but guaranteeing that a connection exists on that bundle is the more difficult part. Or even, I should actually rephrase that. If you can prove the bundle is stable, you even know the connection exists, but finding it is the hard part explicitly. So yeah, for many classes of examples, we actually know via Kobayashi-Hitchin that they are stable bundles in the right topological families over the manifolds we're considering.
Right. Thanks.
I was wondering,
Okay.
Mark, did you want to ask something? Go ahead, please.
I was just wondering whether the nearly Kähler SQ3 structures are something that you had contemplated at all.
One certainly could. I have not looked at that, but I would imagine that the setup could be very similar.
I mean, the manifolds on which they're known to exist are very limited right now.
Agreed. And that's true of the SU3 structures as well, right? So in our paper, we took this very simple class that we knew a solution existed due to Fabian and collaborators as a proof of principle. But again, if you're just sort of doing this in a vacuum, you have to decide, what you interpret in the results. So clearly having a more robust theoretical framework to give you existence proofs or arguments that you expect solutions to exist of a certain type would be great. I.e. analogs of Yau's theorem.
For the Strominger system, you have some of those, at least in some limiting behavior.
I'm sorry, you just broke up slightly. Could you repeat that?
I mean, there are some perturbation results for solutions of Strominger system by perturbing away from.
Mm-hmm.
So
very, very similar in spirit to the one I wrote down. So yes, indeed, you're starting with a simple algebraic manifold that's close to Calabi-Yau, and you can try and perturb the structure away.
But in general,
yeah.
But nearly Kähler, you don't have something like that, except that we found two, a different nearly Kähler structure on S6 and on S3, the standard ones, and in some sense they're not too far away from the standard ones.
Yeah, if you have a class of manifolds to consider, right? If you can algebraically control where you want to be sampling points and integrating stuff, that's potentially in the game. So,
Sorry, Mark, what did you say just then?
Yeah, I just said, well, if you can't do it on the 6th sphere, then that's probably a reasonable place to start.
Yep.
Sorry, Bobby, you.
Yeah, well, I was going to, there's this long-standing conjecture of Edward and myself about nearly Kähler metrics on weighted CP3 with weights PPQQ. So that one is, very much
expected
complex.
To be well behaved, yeah.
But it does have orbifold singularities. So I don't know how those would complicate matters, but I guess you would have to take your sample points away from the orbifold singularities.
Yeah, that's an interesting question. I mean, this was touched on in Mike's talk yesterday, and some of the work of James Gray and Wei Kui looked at this a little bit, even in the Calabi-Yau context. Near say the conifold point, what do you expect in terms of, do the numeric algorithms still converge even near those singular points? So they were looking at Donaldson or the same approach as Heterodic and Nassar. And yeah, your existence theorems might be a bit fuzzy near those points, but in practice, it seems for a lot of the existing algorithms, you actually still get reasonable stuff close to these singular points. So yeah, it would be a good question to explore further, I think.
Well, when this Simon's collaboration first started, I offered, I think, a case of wine in the end for anyone that could come up with an existence proof of those nearly Kähler metrics on weighted CP3. So if you are able to show that you could get numerically close to such a metric, then maybe half a case of wine would be.
There you go, an incentivized problem. Sounds good.
But anyway, related to that question, I was also wondering about, does one gain anything by choosing specific points in the sample set? I'm presuming that you're choosing random. You
That's
have
right,
something
yeah.
like 10 to the 5 points randomly. However, you know, if you think about, I don't know, if we take the example of the quintic, which has, you know, something like 200 non-trivial homology cycles. We know there's a basis for the homology which consists of like 200 cycles, and if you took, and most of those are in middle dimension, so if you took them to be, if you set up the problem so that they were generated by, or some significant number of them were generated by Manifold singularities, for example. I wonder if by taking the points on those locally, you know, locally deformed conifolds, that would you actually gain anything in this business?
Interesting question. I do not know in the specific example that you're illustrating there. Certainly the question of what points, so, you know, near singularities or the resolution of those singularities, you could hope to see a particular structure. In addition, the question of which points is very much tied to how much symmetry you're tuning into this manifold. And something that I personally find actually exciting about the machine learning approach is that it seems much less dependent on that symmetry than previous approaches. So certainly in the work that I did on, you know, implementing Donaldson algorithm a decade ago, I mean, we were very tied to tuning, you know, highly symmetric Calabi-Yau's in order to get all these algorithms to finish, which for practical purposes is not great. So yeah, in that case, you know, you can certainly speed things up, I guess is what I'm trying to say, by, you know, the tuning of special Calabi-Yau's and the points therein. A question more broadly about whether you could learn something from particular sampling, I don't know, but interesting question.
Because I'm just thinking that maybe this is more appropriate for the discussion session anyway, but you know, if you, I mean, this might be a way to make contact with analytic gluing techniques and constructions.
Twisted, connected sum, etc.
Well, not, yeah, I mean, even just like standard gluing constructions, you know, like, you know, let me give an example. If you just consider the Kuma construction of hyperkähler metrics on resolutions of T4 mod Z2, my guess is that if you did this, if you set that up within this, you know, within a numerical framework, far away, if your points that you're sampling are far away from the locally Iguchi-Hansen metrics, you're not going to gain much. So it could be a way of connecting numerical to analytic approaches.
Yeah, I see the idea. I have no idea, but it's a good question.
Maybe, Lara, a quick question related to sampling, since Bobby brought it up. Have you guys looked into other potential sampling algorithms, or how you might use a neural network to actually do the sampling in an intelligent way, like an active learning or something like that?
It's a good question. I may defer this one to Sven and Fabian. I have not. In previous implementations of Donaldson that I've worked with, we did try various numeric integration techniques, you know, adaptive mesh integration, different plans. And I mean, there's definitely room to optimize there. I don't think in what we did, you know, we were focused on that, but yeah. I don't know if Sven or Fabian wants to comment on if you have intuition that one would buy you something in particular.
Well, I can say a few things. So when you do the numerical integration, it's actually necessary to know the distribution of points with respect, I mean, the random distribution of points. To generate a set of points, you need to know the measure underlying this distribution. And there's a construction mechanism due to Selvidge and Schiffman, which sort of tells you when you take the Fubini-Studi metric, how you generate a sample of points that is a random with respect to the round measure that is given by the Fubini-Studi metric. And then when you sort of take these points and find points in the Calabi-Yau, this helps you do the numerical integration. If you do not know the distribution of the measure with respect to which your points are distributed randomly in the Calabi-Yau, Monte Carlo numerical integration is much harder. So having said that, you could, of course, still just sample any point somewhere on your Calabi-Yau, train it with it, and then later to do the numerical integration, you could sort of use this way we described of sort of computing the weights and doing the Monte Carlo. But during training, you're just imposing, in some sense, that j cubed equals omega squared point-wise. So this has to be true at any point. So you could, for training, you could indeed do what you said, do some active learning or adversarial learning, where you try to find points where your network is doing behaving poorly, and then sort of optimize it there, and then in the end to compute sort of the measures to say how well you're doing the sigma loss that Lara was giving, or even integrate the Ricci, compute a Ricci tensor and integrate that to see how close to Ricci flatness you are. Then you would have to rely on knowing the distribution of points.
Mm-hmm.
I don't know, maybe Sven wants to add to that.
Yeah, maybe just, these were already excellent points. Just to add two things. So one is, if you're looking at the psi dependence, for instance, of our results that Lara was presenting, you saw that it really mattered where we are choosing the psi from in order to train and see the accuracy.
That's why I was asking.
And so that definitely has an effect. So now, if you're talking about sampling points on the manifold itself, you're more sensitive then to that region. I mean, you can adapt the measure appropriately, but you will learn that that region that you're sampling more prominently better. You will approximate it better. That's the intuition behind the approximations you're getting. And then you can envision, obviously, to do certain schemes, as you're alluding to, and Fabian also mentioned. Now, we haven't played these games significantly yet, but that's definitely something. I want to, but this maybe for the discussion later, I want to understand more what Bobby was saying also in the connection with analytic stuff, what he was with the gluing techniques, what he had in mind. But we can maybe discuss this later.
Can I ask you a quick question? Thanks for the wonderful talk, Lara. It was really nice. You touched upon various things, and a random question came to mind. So you suggested that that symmetries play an important role in the discovery of this metric. Namely, it essentially reduces the parameter space in your optimization problem, right? Now,
or at least historically, yeah. Mm-hmm.
That's right. That's right. And this is something that's also known in the ML community, that as you incorporate more symmetries, your parameter space is essentially reducing by some function of the order of the group. So here in this case, when you're discovering moduli dependent metrics, so as you move in your complex structure moduli space, it is well known that there are special loci where their symmetries are kind of enhanced. Is there a way of dynamically incorporating this into your algorithm for determining the metric?
Let me make sure I'm understanding the question. So, I mean, my motivation actually was, in some sense, I want to drop the special symmetries because for, sort of pheno purposes, they're pretty artificial. So from my motivation, I was actually hoping that we did not have to rely on them as strongly as we had in the past. But I guess your question is there a way dynamically in the network structure to, when you happen to hit a certain point, to use that to efficiently reduce your parameter space?
Exactly. It's sort of, the motivation is that I've seen in the ML community that the tendency is less to discover symmetries and more to incorporate symmetries in your problem, because the optimization problem is much simpler then.
Sure.
So,
of course,
yeah, that's exactly what I meant.
Yeah, I mean, it's a good question. Again, I think for applications that you're really going to want to use this for, probably you're not going to have high degrees of symmetries. I think they're a little bit artificial. But certainly if you impose symmetries, and if you know that you're starting within, a subregion for which you have them, which, as I said, I mean, when we looked at implementations of Donaldson algorithm, if you do the stuff that Hedrick and Nassar did, this has been highly used to streamline the computations in the past. So people have imposed not just the freely acting symmetries on the quintic, for example, but, like full, very, lots of fixed point symmetries on these same manifolds to try and just reduce the parameter space as much as possible. certainly you can speed things up with that. I mean, it is undeniably easier to work at points of very high symmetry, but I would say, again, motivation-wise, I think that's not where you want to go with these algorithms. I think you want to move back to more general points if you can.
Can I